Thank you very much, Mark. Good morning, everybody, and thank you very much for inviting me to give this talk to you. It's about weather prediction and the scalability challenge. And of course, I am particularly delighted that this is taking place in Stockholm, where I have spent most of my working life. So ECMWF, European Centre for Medium Range Weather Forecasts. I guess we are a little bit known in the HPC community because we do run a fairly large HPC facility. And we are also well known in the meteorological community. But in society in general, I think we are completely unknown. Nobody ever heard about ECMWF. But the weather services, the national weather services, those are very well known in most societies. They deliver forecasts to the public every day. But of course, they have to base these forecasts on something. And in Europe, it was decided more than 40 years ago that a European centre should be established to deliver medium-range weather forecasts for the benefit of the member state Met services. And that was ECMWF. By medium range was meant forecasts 3 to 10 days ahead. At that time, you could do useful forecasts maybe 2 days ahead, not more than that. And the goal was set to do it 10 days ahead. That was a very bold goal in the 1970s. But ECMWF got up and running in the end of the 70s, and the first forecasts were delivered. And it turned out that they had a quality that was superior to everything else that was available. And it's continued like that since then. ECMWF has been producing weather forecast quality which is really unrivaled around the world. And the weather services of our member states are using it every day for their operational forecasting. So what I thought I would do here today is first to give you an overview of the way we do weather forecasting, how we construct our models, how we use the observations. And then I will talk about the scalability challenge, which is a thing we really have in common with the high-performance computational community. We have to be able to use the computer architectures of the future in a much more efficient way. Otherwise, we will be wasting a lot of resources. So the member states of ECMWF, you can see on this map, the dark blue are the full member states, and the light blue are the so-called cooperating or collaborating states. So as you can see, almost all countries in Europe are members of ECMWF and get our forecasts every day. And many of these countries do not have the global modeling capability required to do medium-range weather forecasting. They totally rely on us for the forecast production. The three big countries, France, UK, and Germany, do have capability themselves also to do that. So to some extent, we're working a little bit in parallel with the weather services of the three big countries. But for the small countries in Europe, ECMWF, I think, is absolutely essential. ECMWF has also been important in leading the way for new methods in weather forecasting. New algorithms for doing various things have been developed at ECMWF and have then spread both to the member states and around the world. But having said that, of course, we also at ECMWF depend a lot on what's going on in the science community around us. We pick up ideas from the US, we pick up ideas from Japan and implement it in our forecasting system because we think it's good and it benefits the quality of our weather forecasts. Just to give you a few numbers about the size, there are 34 member and cooperating states. We have about 300 staff working in Reading in the UK, where we are located. And these 300 staff come from around 30 countries. And then, of course, we have partnerships around the world. The funding of ECMWF, it is an intergovernmental organization. It was established in the 70s under so-called OECD framework. It's not an EU organization, it's an OECD organization. And each country contributes proportional to its gross national product. So we establish a budget every year, and then it goes through our council, and if there is a so-called double two-thirds majority vote, then it's in place, and then the member states have to pay up. And this is a process that continues from year to year. It has been very stable. We have been able to expand during this 40-year period. Nowadays, we also have funding from a number of other sources. We have research projects, we have EU projects, Horizon 2020, FP7, we have other nationally funded research projects. We have funding from the satellite organizations, from ESA, European Space Agency, and EUMETSAT, the meteorological Space Organization, and we also have funding from a couple of other sources around the world. We also have commercial income. Our forecasts, we don't really go out and sell them ourselves, but via our member state Met services, our forecasts are sold all around the world, and we get part of that money that comes in. And then, as from last year, or November 2014, we're also running something called the Copernicus Climate Change Services and the Copernicus Atmospheric Monitoring Services. These are EU-funded programs where ECMWF has been delegated the authority to run these projects. And actually, in the future, that will make up a substantial fraction of our total budget. So over the years, ECMWF has expanded into various domains, but we still have a very clear focus on the medium-range weather forecasts. That's what we're supposed to deliver. That's where our research goes to improve the medium-range weather forecasts. That's where we focus our attention. So this is a list of the different activities we have, where the global numerical weather forecasts, they come at the top. Supercomputing and data archiving is, of course, also a large part of our activities. We are also providing supercomputing power for our member states. It's mainly for the Met services. They can use it both for the research and development, and they actually run also operational jobs on our computers. We also have some part of the supercomputing which is for the meteorological research community in Europe, in our member states. And then we have the biggest meteorological data archive in the world, which is used worldwide for a number of things. We have an education and training program. We deliver training courses, both in basic numerical weather prediction, but also in the use of our forecasts and also in computing. We do training and education. And then, as I mentioned, we have the EU activities, the Copernicus Climate and Atmosphere Services. There's something called EFAS, the Flood Alert System, which is part of the emergency management in Europe. And then, finally, more recently, we have also established a scalability program with funding from European Community research money. So all in all, we are expanding into different areas, but I think if you come into the organization and you see what people are focused on, everybody is very much aware of our main goal. We have to improve the weather forecast. It's a very, very clear goal for the organization, which is, I think, quite a nice way to work with such a clear goal for what you're supposed to do. So I won't say too much technically about our computers because I do not know much about it. I mean, I'm not a specialist in computers. I come from meteorology science. But we have Cray XC30 supercomputers with about 90,000 cores, and we have 2 of these machines which are running in parallel. We're always using one, mainly for operations. We are delivering the forecasts 24/7, 365 days of the year. And we have an extremely high reliability in terms of delivery of the forecast information. And that's actually quite important to us because our member states are so dependent on getting the forecast information on time. When you make a weather forecast, you have to make the computation so quickly that you can deliver the forecast before the information is out of date. That's sort of the name of the game. And it means, I mean, we get observations continuously. We do computations overnight, and then something like 4 or 5 o'clock in the morning, we deliver the forecasts which are based on the observations that were made around midnight. So that's sort of the time span we have to process all the data, to do the computations, and distribute the results to our member state Met services. And then we do this in a cycle, and it's actually 4 times a day that we repeat this cycle. So having the computing capacity, having a reliable and robust system is extremely important for us. That's why we have 2 machines in parallel. If one falls over, we can always revert to the second one. But of course, we are not using all of the computing resources for the operational forecasting. We're also using a lot of it for research and development. We are constantly looking at new ways of improving the methods, and we're running huge experiments on the computers to see how it works. To test new methods, to verify against the observations, to build up new forecast systems, and then introduce them into operations. So ECMWF is really a service with a very high research profile, as well as reliable operational delivery of forecasts. To me, that's a fascinating part of meteorology, that you can work with science, which is frontline in terms of the research, and at the same time you can check it every day against the weather, what actually happened. I could have brought a forecast for Stockholm with me. I actually forgot to do that. But if I would have done it, a forecast from a week ago, you would have seen that it actually was quite accurate. You've had a couple of rainy days here in Stockholm. I knew that already last week. And it'll be a beautiful weekend for those of you who are staying on in Stockholm. I can almost guarantee that. Right. So what are the kind of computer models we use? Well, I thought I would just give you a very brief overview of the way we do things. So our forecast model is global. The weather is global. What happens with the weather here in Stockholm a week ahead depends on the weather on the other side of the Earth. You have to use a global model to do medium-range weather forecasting. Our present highest resolution system runs on a 9-kilometer grid. So we have 9-kilometer spacing between the grid points all over the globe. That's a lot of grid points. And we use 137 vertical levels in our model today. And the levels are unevenly distributed. We have a high resolution close to the surface, and then it gets a bit wider as we go up towards the top of the atmosphere. The top of our model is about 100 kilometers above the surface. At each of these grid points, we calculate using Newton's second law of motion, thermodynamics, basic radiation physics, wind, temperature, pressure, humidity, clouds, and precipitation. The normal weather variables that you can use basic physics to construct a mathematical model that you can then integrate forward in time to predict the weather. Having a 9-kilometer grid, you can describe a lot, but of course not everything that's happening in the atmosphere. There is a lot of weather going on between the grid points. I should also say that the numerical method we're using is actually a spectral technique. We are describing all these fields in terms of spectral fields on the globe, using Fourier and Legendre expansions. But then we flip back and forth between a grid point description and the spectral representation every time step. It turns out to be the most efficient way of doing it. And in the grid point domain, we also calculate what's happening between the grid points. If you look at a cloud in the atmosphere, for instance, there are no clouds which are homogeneous over a 9-kilometer scale. They are very small scale. Turbulent eddies are small scale. Lots of small scale things in the atmosphere happen which cannot be explicitly described on the grid. And these are what we call in the jargon physical processes in the atmosphere. And this is just showing you some of these physical processes going on between the grid points, which we have to parameterize, as we say it. We have to construct parametrical models of how the heat fluxes and momentum fluxes resulting from these processes affect what's happening on the resolved grid. So you have clouds, deep convection, shallow convection. You have radiation, short-wave radiation from the sun, long-wave infrared radiation into space. You have turbulent diffusion close to the surface. You have latent heat flux and sensible heat flux. Latent heat flux, in other words, is flux of water vapor from the surface to the atmosphere. And then you also have the effect of orography. Mountains have a profound effect on the circulation of the atmosphere. And a lot of things happening on the small scales are very important on the large scales and have to be parametrized, so-called subgrid scale orographic drag. In our present model, we also have a little bit of chemistry. We have a description of ozone, which is still quite primitive, but it's there, and also methane we have a model for. We couple the atmosphere model also to an ocean model. What happens in the ocean is quite important for the atmosphere. And actually, even in the medium range, 2 to 10 days, in the tropics, the dynamics of the ocean couples very tightly with the dynamics of the atmosphere. So we have to have a comprehensive, what we call an Earth system model, describing the atmospheric processes where the atmosphere is the central box, and then coupled to the ocean and coupled to the land surface. And all of this is included in our computing model, and we use the basic laws of physics to do the computations. To initialize the forecasts, we need observations. So what do we have in terms of observations? Well, to do global forecasts, you have to have a global set of observations. And what is available around the world is shown in this cartoon here. First and foremost, we have the satellites. There are some 70, 80 satellite instruments flying up there with platforms, satellite platforms that have been shot into space through the major space agencies around the world. In Europe, we have EUMETSAT, which is the operational meteorological satellite organization. ESA, European Space Agency, also contribute. In the US, we have NOAA, the National Ocean and Atmospheric Administration. NASA, to some extent, but it's actually mostly NOAA. In Japan, we have JAXA, who are doing the satellites, and we also use more and more Chinese satellites that are coming up. Then there are Russian satellites and Indian satellites as well. So there's a whole range of satellites up there who are constantly observing the atmosphere. Now, these satellites are very high up. We have the polar orbiters, which are about 400 or 500 kilometers above the Earth's surface, and then we have geostationary, and they are 36,000 kilometers above the Earth's surface. What they observe is basically the electromagnetic radiation coming out from the Earth system. And by observing that in different wavelength channels, you can deduce the properties of the atmosphere, temperature, humidity, even wind from the motion of the cloud field. And all this information is continuously fed into our computing system. Then we have the standard old-fashioned surface observations, but they are actually still quite important. And in particular, surface pressure is a vital thing in the atmosphere system to determine the mass distribution of the atmosphere by surface pressure measurements. We also have the radiosondes, which you have here, or the weather balloons. They are not that many, about 600 around the world, launched every 12 hours, giving profiles, vertical profiles of temperature, humidity, pressure, and wind. This is vital information for our model. Even though it's a small set of information, it is high quality in situ observations that we really need to calibrate the satellite data. Then we have commercial aircraft giving us observations. They are very good, but unfortunately they're concentrated along the flight paths over the Atlantic, the North Atlantic, and the Pacific. That's about it. There is almost nothing in the southern hemisphere. We have ships, we have buoys in the ocean, and a lot of other things. So all this observation information comes in every day, and we use it to determine the starting point of the forecasts, the initial state. If we look at the evolution of satellites over the years, going back to the mid-1990s, in this graph you see here how many satellite instruments there were with meteorological information. There were only about 10 of them in the mid-1990s. And actually, in the 1990s, the satellite information that we got was very, very hard to use. I mean, to use electromagnetic wavelength information and to invert that into temperature and humidity is not a trivial problem. And we really weren't able to do that in the 1990s. There were some new methods developed around the year 2000 which greatly enhanced our capability of using satellite data. And you also see that the number of instruments has accelerated enormously. And today, 2016, there are something like 70 instruments out there which we're using. And the projections to 2018 is that it will continue to expand, and that goes into the 2020s as well. So satellite data is the vast majority. It's more than 98% of the data we get come from satellites. However, we have a filtering problem with satellites. Because of the mass of information we get, we have to be very careful in selecting the data that actually contains the information we want. So part of the processing we do is actually to throw out some 90% of the satellite data. But we have to throw out the right part, the ones that we're not interested in. And of course, we have to develop methods to use more and more of the satellite data. After all, it's very, very expensive data. Just as a comparison, the European Meteorological Satellite Organization get about 10 times as much money as we do. Satellites are really expensive. To use the satellite data, and what made it possible to use satellite data, was the development of a new assimilation method called four-dimensional variational assimilation. This was pioneered at ECMWF in the 1990s, and it's still today the mainstay of what we call data assimilation. And without being too technical, I thought I would still try to explain to you a little bit about how this works, because it is really essential to how we do weather prediction. So we work with what we call assimilation windows, which you see here on the horizontal axis. A 12-hour window over which we can take all the observations we can get. We also have an old forecast, a forecast resulting from a previous initial state, let's say 12 hours earlier. And the orange line you see here, the thick orange line, is the best estimate from a previous forecast of the state of the atmosphere. In addition to this best estimate, we also do perturbations. We do an ensemble of estimates of sort of a likelihood distribution of atmospheric states, perturbing the observations a little bit to take into account their uncertainty, and also perturbing the model. We can produce a set of preliminary forecasts, which then also gives us a measure of the uncertainty of these forecasts over the assimilation windows. And these are short-range forecasts, not more than 24 hours. Then we have observations coming in, and here I have just drawn, as an example, 2 observations, which also have uncertainty limits. Observations are not exact, they're also uncertain. But if you have the uncertainty of what we call the first guess, as well as the uncertainty of the observation, you can then use statistical methods, an optimization problem, where you can infer what the optimal state of your atmospheric model should be. And this is data assimilation. And what we do then is that we adjust a little bit the state at the start of the assimilation window, and then we do a new set of ensembles, and we match it to the observations. And this is done iteratively over this 12-hour window. Now, this assimilation technique is sequential, which means that it's quite tricky to parallelize it. So one of our scalability challenges, because we use a lot of computing power in doing data assimilation, is to make this parallel, is to make it scalable. And that's one of our main activities at ECMWF, to develop new methods for parallelizing our handling of observation information to find the most optimal initial state for our forecasts. So when we have completed this, and we have reached the middle of this figure here, then we have both an estimate of the most likely state of the atmosphere, as well as a probability distribution around it. And then we use that, not just to launch one forecast, but to launch 50 forecasts in parallel to also determine the uncertainty in the forecast. In the beginning of the forecast, it's a fairly small uncertainty, but of course, as we reach later in the forecast, the uncertainty becomes bigger and bigger, because the atmosphere is chaotic. Any small perturbation in the initial state will sooner or later result in something that affects the whole global atmosphere, and we will be in a very different state. So we can take our forecasts that we produce with this method and compare them to reality every day. And what you see here is the time evolution of our forecast quality, both as a function of forecast lead time in days, and also for a year, a whole year of forecasts from 1990, 2000, and 2010. And on the vertical axis, you have the error at the 500 hectopascal level. We use pressure as the vertical coordinate. So we rather use the height of the pressure surface than the pressure at a certain height. So that's why the error is in meters. So it's the height of the level where the pressure is 500 millibars. At the initial state, the error is small, but it's not zero. And you can see that over time, from 1990 to 2010, there has been a substantial reduction of the initial state error. Then, of course, as the forecast progresses, the error increases, and sooner or later, you will reach an asymptotic value of the error, when sort of chaos has set in. That happens after 15 to 20 days. It's beyond the 10-day timescale. But what you see is that we have a constant improvement of the forecast accuracy. But the model itself is, of course, not perfect either. So we also have an error growth due to the model. It's both the error in the initial state and the error in the model that produces an error in the forecasts. Inevitable. But if we look at a certain acceptable error level, which is judged to be around 60 meters in RMS errors, we see that the range where we reach this threshold error has moved from about 4.5 days in the 1990s up to something like 6.5 days in 2010, and now we are somewhere hovering around 7 days. So the forecast quality has continuously improved in time due to improvements in the model, due to more satellite data, and of course due to more powerful computers, so we can make the models more and more accurate. If we look a little bit more in detail of how this useful forecast range has evolved month by month from the end of the 1990s and up until today, actually, you get a curve that looks like this. So on the vertical axis, you have the number of useful forecast days, and on the horizontal axis, you have the year. The blue curve are averages for every month. And this is now for Northern Hemisphere, I should say also. You can see that there is a systematic seasonal cycle in the forecast quality. Forecasts in winter are generally better than forecasts in summer. That's a basic property of the atmosphere. You have more intense system, more large-scale systems. It's easier to observe. You have more energy in the atmosphere. You also see that around the year 2010, 2011, our forecasts were exceptionally good. The winter of 2010 was absolutely fantastic. We could make forecasts up to 2 weeks, which were almost perfect. We introduced a new model at the end of 2009, but I'm afraid to say it was not the new model that did this. It was just that the atmosphere was kind to us. The flow situation was more predictable in the winter of 2010, 2011. And this happened again in 2011, 2012. Since then, the atmosphere has not been so kind to us. And even if we have constantly improved the model, it looks like we have a little bit of a flattening out of this red curve, which is the moving 12-month average. I joined ECMWF in 2009. There was a magnificent jump in the beginning, and since then nothing has happened, you could say, which is a bit unfortunate. But it is due to the fact that the atmosphere was very kind to us in 2010, 2011. We are still working hard with improving the model, and we can actually normalize this by comparing to other forecast centers and how well they are doing in the same measure. So these curves here, they show you the quality in terms of the number of predictable days. From ECMWF is the red curve, the top one. The black dotted line is a reference system, which we also run. We basically take the forecast system we had in the early 2000s as a baseline, and then we use that without changing it, just to see what the quality would have been if the system had been constant since 2003. And we see that we are systematically better than that reference system. And the distance between the red curve and this black dotted curve keeps improving or keeps widening all the time. And even in the reference system, the forecasts in 2010 and 2011 were exceptionally good. The other curves show results from our competitors. There are, of course, other forecasting centers around the world doing the same thing. The blue curve is the UK Met Office, situated in Exeter in the UK. They also have a very good system. They are slightly behind us, but they are producing forecasts of a very good skill. Then the green curve is NCEP. That's the National Weather Service in the United States. And then you have the Japanese, which is the yellow or orange curve. And then you have CMC, which is the Canadian model, also for comparison. So you see that everybody is improving their forecast quality all the time. It's free and open scientific exchange. Everybody can pick up everybody else's ideas. But of course, you have an operational system which you use for operational forecasting, where you can really intercompare the quality of the forecasts. So in recent time, we have been picking up again a bit, but so have the others. So that's probably due to the kindness of the atmosphere. But the important thing is the distance to the reference system. And if you look at that, you can really see that things are systematically improving all the time. Our forecasts are getting better and better. And the way we have done this is by improving the resolution of the model, making the distance between the grid points smaller and smaller, improving the assimilation methods, use of the observational data, improving the descriptions of the physical processes. All this has to go hand in hand to improve the quality of the whole forecast system. And of course, the resolution we use is very much limited by the available computing power. The number of grid points we have in our model basically determines the size of the computer we need to make forecasts within the time slot we have available to make a forecast to deliver it to our users. And if we summarize the challenges for the future that we have, if we look at today, the volume of observations that we process every day is about 40 million, with a major part coming from satellites. 98%, it says here, from 60 different satellite instruments. The models that we use with a 9-kilometer grid, it's about 10 million grid points on each horizontal surface. It's about 100 levels, or 137 to be exact. And we have about 10 prognostic variables. So in total, we have 10 to the power of 10 degrees of freedom in our model, which have to be handled by a computing system. And these then describe physical parameters of the atmosphere. We also have a special model for the ocean surface waves, and then, as I mentioned, also an ocean model. If we look into the future, what will happen tomorrow? Well, satellites will continue to increase. There will be more and more satellites, and the instruments on the satellites will deliver more and more data. An estimate is that the volume of the satellite data will go up from 4 times 10 to the 7 to somewhere around 10 to the power of 8 in terms of magnitude. And there will be something like 80 different satellite instruments 5 or perhaps 10 years from now. If you look at the models, if we look at the progress that has been made in resolution, tomorrow we will have roughly 500 million grid points. We will have something like 200 vertical levels, and there could be something like 100 prognostic variables. We have in our plans to include more and more of the chemical properties of the atmosphere, the concentration of aerosols, particles in the atmosphere, concentration of gases, both reactive gases and greenhouse gases, and this will increase the number of variables we have in the model. All of this then, if you sum it up, means that the observations will increase by about a factor of 5, and the model complexity will increase by about a factor of 1,000. That's a lot. And we know that with the computers we'll have about 10 years from now, we will not be able to fit this in with the methods we're using today. We have a fundamental scalability challenge to be able to do this, but in a smarter way with tomorrow's computers. Another way to visualize this is that you can also get, of course, benefits from it. And if we look along these 3 axes, model complexity, model resolution, and compute power. Model resolution is here visualized by the resolution of a tropical cyclone. On the very most right-hand side, that is actually a picture of a tropical cyclone, but using the model resolution of the 1980s. And down at the bottom is a picture of the same tropical cyclone using the model resolution of tomorrow. It's order of kilometer scale resolution. So you can really see how you can represent much, much better a very significant phenomenon in the atmosphere. Model complexity is this Earth system. Not just having the standard physical parameters of the atmosphere, but also the chemical composition. Land surface. There are lots of things that you can include from the land surface that affect forecast quality. And the ocean. The interaction between the atmosphere and the ocean is another challenge in the future, how to improve that. To go towards a more comprehensive Earth system model is also a requirement for the future. The red curve is what would happen if we just continue to do as we do today. If we increase the model complexity and we increase the model resolution, the compute power that we need would go up dramatically. The green curve is the path that we are allowed, given the constraints of the supercomputer power available. We have to follow the green curve instead of the red curve. And another aspect, which also comes into model complexity, is the ensemble method. As I showed you, we are not just doing one forecast shot into the future, we're doing 50 in parallel. We've chosen the number 50 because it's reasonable, given today's computing power. We would want to do many more. Hundreds of parallel runs would be a more efficient way of predicting the uncertainty of the forecast. But of course, that also costs in computing power. But it is rather trivial to parallelize it on a computer, the ensemble method. So that's another part of the model complexity axis, which also comes in to the equation of how we can improve the forecast quality by using future computer power in a more efficient way. Now, about a year ago, a report was published that assessed the scalability of a number of different so-called dynamical cores of models that are used all around the world. It's called the AVEC report from Michalakis et al. Michalakis works at the National Center for Atmospheric Research in the US. And this is now an HPC type of graph, which shows you on the horizontal axis the number of cores on a Cray XC30, going all the way out to 139,000 cores. And on the vertical axis, you have the performance of the model, and it is in terms of fraction of what we call the operational threshold. The operational threshold is that you should be able to do a 10-day forecast within 1 hour. That's a 1 on this diagram. So if you're below the 1, then you can use that model for operations. No, sorry, if you're above the 1, sorry, then you can use the model for operations. If you're below the 1, you can't. And then each curve shows the scalability of a number of models. The yellow curve is our present model, the ECMWF model. And the other curves are a number of candidate models in the US for the next forecast system for the National Weather Service. They have done an extensive investigation of different numerical techniques for the dynamical core to see which one will be most efficient for the future. And if you look at this graph, this is also for a 13-kilometer horizontal resolution. Our model is still, in absolute numbers, the most efficient model. It's the fastest model. And also when we compare ourselves to the UK Met Office, we have a much faster model than they have. But it is not particularly scalable. The curve starts to bend off with more and more cores. The other models, in particular the dark blue one at the bottom, this Neptune model, is not very efficient at the moment, but it is very, very scalable. And in that sense, it has more potential for the future. So the scalability of our model is really a problem that we have at the moment. We have to improve the scalability of our basic dynamical core in order to make better use of future computer architectures. And the scalability of this dynamical core comes into all parts of our forecasting process. It, of course, comes into the forecast computations, but it also comes into the data assimilation. We use the same model for data assimilation. We use the same ensemble technique. And an efficient model implies an efficient data assimilation. It also has implications for the distribution of the forecast products. We have to have an efficient way of taking all this model data and distributing it to our users. We are hoping that about 10 years from now, we will be down to 3 kilometers resolution for our main forecasting system. With today's model, this is the green curve now for ECMWF, we are far below the operational threshold. I show you this curve just to show that with the model we have, we can still use some 139,000 cores to do experiments like this. It is possible to run the model on a number of cores. It is possible to do a global model with 3 kilometers resolution, but it is not scalable. We have to push up this green curve to make it more scalable. And once again, the blue curve here, the Neptune model, is almost perfectly scalable, but not very efficient at the moment. But these other curves are still models under development. They have a great potential for improving their absolute efficiency, and they have the scalability, so to say, built into the model from the beginning. So a serious effort that we're doing right now is to look at the scalability of our basic dynamical core. And as I told you, we use a combination of a spectral technique and a grid point technique. We switch back and forth between the spectral and the grid point domain every time step. We believe that the spectral part is essential in the future. And it's because we use so-called semi-Lagrangian, semi-implicit time integration schemes. I guess for some of you, you know what that is. Semi-implicit means that you have to solve a Helmholtz equation at every time step, which is a global problem, which therefore requires a lot of communication. But when you do it in the spectral space, it is very efficient. Semi-Lagrangian time integration is done in the grid point domain, which means that you're following a trajectory in time, and you're, so to say, computing along a Lagrangian trajectory of your model at every time step. That is also an issue for scalability. To do that efficiently, what's the domain you have to look into to compute your semi-Lagrangian trajectory? And then it may be that you don't have to use the same resolution for all the different model components. That you can, so to say, do some things on a coarser grid and other things on a finer grid. And to combine that is another way of improving the scalability of the system. So we are doing a lot of research in that area, and I think I have a slide later on just showing you a couple of examples. But if we look at the efficiency gains that we have to accomplish in the next 10 years in order to remain sort of a viable producer of medium-range weather forecasts, this graph here from Peter Bauer shows you as a function of model resolution going from 30 kilometers and all the way down to 0, and the number of compute cores on the vertical axis on a logarithmic scale. And then you have two ranges here. The top one is for the Ensemble model. That's the parallel runs of a number of different, slightly perturbed versions of our forecast system. We do that at a coarser resolution. And then the lower range is for the single-shot model, which we do at a higher resolution. Today, the Ensemble system has a resolution of 16 kilometers, and that's the dashed green line, while the high-resolution system has a resolution of 9 kilometers. That's the dashed blue line. And today, we are at the top of the scalability range. We haven't done that much work yet on improving the scalability. The range here gives an estimate of what we hope that we can achieve with our scalability program. So when we come to 2025, and the kind of resolutions that we may be running at, if we have an ensemble at 5 kilometers, we would have to use something like more than 1 million cores. And for the single model system, we would have to use even more cores. But we are limited by computing power. We don't think that our member states, or anyone else for that matter, will be paying us an electricity supply more than about 20 megawatts. That's our estimate for the next 10 years. So the power limit at 20 megawatts puts a definite ceiling on where we can be in terms of resolution 10 years from now. And it's mainly a cost issue. So for the high-resolution system, it seems that kilometer scale is unrealistic for the next 10 years. For the single shot, we have to be somewhere around 2 or 3 kilometers. We can't go much further than that. For the ensemble system, a 5-kilometer resolution by 2025 is not unrealistic. It still requires a lot of hard work. We have to be at the bottom of the scalability curve to reach this goal. But we think that's achievable. We think that with our scalability program, we can develop new methods which will enable us to reach this 5-kilometer for the ensemble system. So in our 10-year strategy that we've recently developed, a 5-kilometer ensemble is the strategic goal for 2025. And at the same time, to have the compute power that uses around 20 megawatts of electricity. That's where we want to be 10 years from now. And in terms of scalability, we are working on a number of different areas. We use something called the Atlas data structure, which is an efficient way of doing interpolations between grids, which is absolutely essential for especially the semi-Lagrange and time integration. To use unstructured meshes as well to divide our global domain into smaller domains where we can do the computations more locally. The I/O and also the way we design the spectral transforms is another aspect of the scalability program. But we also have to look into the basic equations we are using, the equations of motion, how we formulate them. Today, we're running a hydrostatic model, which means that the vertical velocity or the vertical accelerations are not explicit. They're only implicitly calculated. When you come down to kilometer scale, you probably have to go non-hydrostatic. That's expensive, but we have to do it. Transports, to conserve mass for transport schemes, as we go into more and more chemistry in our model, the transport is also an essential part of the system to have accurate transport calculations. And, of course, keeping the semi-implicit scheme, we have to solve the Helmholtz equation in 3Ds. And to do that efficiently will also require scalability work. And then on top of that, we have, oops, that was not the intention, data assimilation and the coupling between the model physics and the explicit dynamics. Those are also other areas where scalability comes in and where we have work on projects to improve those things. Now, all of this we are doing in a program that involves a lot of collaboration across our member states, but also across Europe, across the community, and with partners around the world. And this final slide here gives you just an image of the type of collaborations that we have set up in our scalability program. This has very much been developed by Peter Bauer over the past two years. And there are three main axes in these diagrams. We are a bit egocentric, putting ECMWF in the middle. But we have our member states, shown here by the different flags, not all of them, but a couple of them. We have the so-called regional modeling consortia in Europe. These are consortia of member states who have decided to jointly develop regional numerical weather prediction systems. So they take our global results and then they force the boundaries of the regional models to produce finer resolution forecasts. There is one called HIRLAM, which is led by the Nordic countries, but also includes Spain, Ireland, and the Netherlands. There is the COSMO consortium, led by the German Weather Service, also including Russia and Poland, and a couple of other countries in Europe. And then there is the Aladdin consortium, which is the biggest one, which is led by Météo France, the French Weather Service, including Southern European countries and also Eastern European countries. So these regional modeling consortia also have the scalability challenge. They're also working together with us to improve the scalability of the numerical weather forecasting models. Then up to the left, you have the hardware providers. They're also involved in our scalability program. And then up to the right, you have organizations, including then the European Commission, NCAR, the National Center for Atmospheric Research in the US, NCEP, National Centers for Environmental Prediction, also the US, and DKRZ, the German Computing Center for Climate Research. Climate modeling, they have exactly the same problem as we. They're using the same models. And I think I can say safely in this room that to do good climate modeling, you have to do weather prediction. There's no way around it. The only way you can verify a climate model is by using it for weather prediction. But if you do good weather prediction, then you can have some confidence in the climate projections that you make from the model. So they're also involved. We see this as an essential network for our future development. We have to solve the scalability problem, otherwise we are dead in the future. So this is really essential for us and for our community to then also collaborate with the HPC community around the world to achieve better scalability of the models that we're using. And I have understood that there's something called numerical dwarfs, which are snippets of code that everybody uses, and you can use those as units to make more efficient. And I think we have produced so far 4 or 5 dwarfs in our special model domain that we have submitted to some of these projects that are looking more generally at dwarfs from all sorts of application areas. And we really want to contribute to this, and we want to learn from others how we can improve our computational efficiency. So, to summarize, to get a good weather forecast, you have to have an accurate initial state, and you have to have an accurate model. There's no way around that. These 2 things have to be fulfilled, and that's where we're putting our research efforts. Ensemble methods are also essential to assess the uncertainty of weather forecasts. And the future challenges we have are in Earth system modeling and scalability. I think those are the 2 main challenges for us in the future. Of course, on top of that, we also have a lot of sub-challenges. But these are the 2 main areas that we have to put increased effort on. So with that, I'll show you the flags in our meeting room, which I think Mark mentioned here, just introducing me. This is from our beautiful 1970-style council room, where all the decisions are made about our budget and our future. Thank you very much.